Diabetes is a metabolic disease which causes high blood sugar in the human body. This is due to either a lack of insulin production in the pancreas, which is referred to as type 1 diabetes, or a lack of response from the human body to the insulin that is already being produced, referred to as type 2. The WHO has labelled diabetes as a growing epidemic, with type 2 accounting for 90% of all cases. Type 2 is associated with a reduced life expectancy of approximately 10 years, as well as a fourfold increase in the likelihood of cardiovascular disease. These are just some of the conditions type 2 diabetes can cause. The total amount of deaths due to diabetes is estimated to increase by 50% in the next 10 years, and by 80% in developed countries, even though it can be easily treatable through a healthy diet and a physical activity. Although these methods are all effective at reducing the blood sugar levels of the human body, anti-hyperglycemic drugs are vital in order to decrease blood sugar levels. Metformin is an anti-diabetic drug which is effective at decreasing high blood sugar levels of type 2 sufferers of diabetes. It is especially effective at decreasing the blood sugar levels of people who are clinically obese, but who also have normal kidney functions. Metformin acts in the presence of copper by binding to complex 1 of the mitochondrion. This causes signaling pathways to be enhanced, which results in decreased hepatic gluconeogenesis. This reduction in gluconeogenesis is what is believed to account for much of the drug's anti-diabetic properties. The paper, Cellular Responses to the Metal Binding Properties of Metformin, investigates the effect the presence of copper had on metformin inhibition and the future possibilities metformin could have on the treatment of diabetes. We spoke to Dr. Alan Prescott to find out more.
What was your role during the investigation and what got you interested in being involved with the research?
Okay, so I was mainly involved in the microscopy side, so we were interested in where the site of action of this metformin drug, and we thought it might be in the mitochondria. So in order to prove that, obviously you then have to sort of look for localization of the mitochondria, and we used a reporter, a copper sensitive reporter, which showed the levels of mitochondrial copper.
How was the pi electron ring delocalization significant to the binding effects of metformin?
Well, as I understand it, I think that the interaction, the way in which metformin works is it's able to build a very strong affinity with copper, and is able then to pull copper off proteins, and it takes like 2 metformin molecules to form this ring structure, which actually is able to pull off the copper. So there's a very high affinity for copper.
So what was the experimental procedure for the separate experiment involving pioglitazone?
As I remember, I think the experimental procedures were pretty much the same as far as the microscopy was concerned. I mean, basically what you do is you take the cells and you load them with the copper reporter, and then you wash out the excess. It's a membrane permeable compound, so it loads into the cells, and it's a fluorescent molecule that becomes fluorescent when it loses fluorescence when it's in the presence of free copper, but once copper is lost or sequestered, then it becomes more fluorescent. So you load that into the cell, and then you administer the particular drug or compound that you're interested in, whether it's metformin or any of the other compounds that we tested. Some of them were simply positive controls that we knew would have an effect on copper, so we had to put some positive controls actually to prove that what the mechanism that metformin was working through. So essentially we had the compound, and then you take the cells, put them live in under a microscope, keeping them at 37 degrees and in 5% CO2 as they would be in the incubator, and then you could just image them fluorescently using fluorescence microscope.
What do these results tell us about metformin's effect on type 2 diabetes, and are there any side effects?
Well, what it tells us, I think, is that metformin is not working through the mechanisms that were originally thought, or at least it's not solely working through those mechanisms. So what it gives us is an opportunity to try to develop new compounds which might be based on metformin, which may, for instance, have a better copper sequestering ability than perhaps metformin. So it's now we understand at least slightly better the mechanism by which metformin works. It allows us then to take metformin as a lead compound and design other drugs around that compound to get a better, more efficient drugs. Maybe, as you say, drugs with a less side effects, or the side effects of metformin are not so severe.
So what results from the experiments can be further used in order to help with the treatment of type 2 diabetes?
Well, essentially, that's what we'd hope to do. I mean, we'd hope to demonstrate that we can understand fully the mechanism, and we don't actually have, we haven't got every nut and bolt in place in terms of the mechanism of action of metformin. It's only a preliminary publication. So we hope we'll get more idea of what effect it has on the mitochondria of the cells, whether it actually affects their dynamics or their positioning and or their fission and movement in the cells. And then we then have a sort of bioassay in which we can test other compounds. So we can design other compounds, or chemists can design other compounds based around metformin, which may have a much better activity, and we can test those in a sort of an in vitro bioassay on cells, which then obviously gives us some clue as to how much better they work.
Okay. And how can this study be used to further understand the effects of other drugs and their metal binding properties?
Well, I mean, these fluorescence indicators. There are other indicators around for other metals, and so you could potentially look at other compounds using exactly the same type of assay. So you could actually use sensors for, say, zinc or for lead or any particular metal that you're interested in, and then you could then test other drugs and see whether they were working through the similar mechanism of action.
And for other diseases as well, like cardiovascular diseases and...
Yeah, I mean, if that's where the way that some of the other drugs are working, I mean, there are drugs related to metformin which might be working, through exactly the same mechanism, which maybe not through sequestering copper, but maybe sequestering other elements which are necessary necessary to the cell.
As a result of this investigation, it is entirely possible that in the future, better, more efficient drugs could be used in order to treat type 2 diabetes, once metformin action becomes fully understood. Other drugs could potentially be used to treat type 2 diabetes, as they may be able to interact with greater efficiency. However, in reality, metformin side effects aren't as serious as other drugs. This means pharmaceutical companies are less likely to want to invest in a drug which they feel is already good enough. There is a lot more to be discovered about type 2 diabetes, but this study has taken the first of many steps to eventually find better treatments and hopefully one day curing diabetes.